The first presentation is by Jonathan Silverstein. He joins us in person here from the University of Pittsburgh. He will present on graphing UMLS. Jonathan, while he's setting up, comes to us from the infrastructure component, which is a larger team, also working very closely with the tools component at CMU and the Pittsburgh Supercomputing Center and the University of Pittsburgh. And again, it's a pleasure to have him here in person.
Thanks, it's great to be here. I think everyone can hopefully see this and hear me okay. And what I want to do is show you a set of very practical things and theoretical things intermeshed in the same time. But this is a collection of things, not a formal presentation. And so the hope is to get through a set of them and leave plenty of time to ask all kinds of complicated questions. But I put this up first as the service architecture to give us some perspective. So the sort of core business of our component of HuBMAP is to make sure that this stuff can work, that terabytes of data can come through, can be put where they belong, and that it's a flexible infrastructure working with my multiple PI, other colleague, Nick Nystrom, who I don't believe is here today online, but at the Pittsburgh Supercomputing Center, where these things will get I'm trying to see if the mouse is, it is, okay, good. Things will get stored, things will come in, they will have all of these types of work that we've been describing happening amongst this large consortium of people, very much like many of the ones we've heard from. But this interesting feature in which we have these other components, the mapping components and the tools components, that will build a whole sets of APIs and tools in layers that will operate over this data. And so I think the ontology issue here, I want to pose in that context. It's one of a much larger set of tool sets that will interoperate in a microservice architecture amongst a whole set of different tools that will pipeline, that will create data levels, that will do these visualizations, all of these things. So I think this sort of larger context is important. Okay, I'm having a challenge because the overlap of the actual presenter thing is in the way of my ability to use the screen, so maybe I can put that somewhere else. Let's see if that's possible. Well, I can always move this down. So that seemed to do something useful. Okay. So another big piece that we've heard some about that I just wanted to, so we have the responsibility for that. Another big piece is provenance. And so the microservices architecture of APIs and the mentioning of provenance are particular purposes as to preview the things I'm going to show you in the ontology frame. This is the basic model, if you will, based on a terrific set of work that's done around provenance using graph databases from one of our European colleagues, Vasa Surgeon, some of you may know. But in any case, he put together a provenance model, which we are building out. And we're also building out a UUID model that will work with the ingest for these, such that all of these entities, whether they're people or sources of data, specimens, that they can be derived one thing as another following this graph provenance. And so we're building these kinds of pieces that we heard some about. So I just want to give some perspective on that. But the main thing that we're going to talk about here is the ontology work. And I want to focus, the title that I gave was Graphing UMLS, and this is really because a pet project that I had built sort of on my own a couple of years ago has hit directly head on with the HuBMAP activity when it came around. And this is really about that little story and what it shows and what it tells us about what we need to do going forward. So this is the Unified Medical Language System reference manual. And what I love about this page is that under 3 there, the thesaurus, it says estimated reading time 29 minutes. Okay, I've spent 25 years on this page. Okay, and maybe 29 years. And the point is that what UMLS has done is they've taken this tremendous ontology space and through 30 years of curation on a model that was workable, has put all of these things in the same model. People often don't think of them this way. They think of them as this vocabulary and that vocabulary, and we heard a lot about this. But the fundamental thing is this is in a strict set of files that all come together, that all follow the same model with over 100 vocabularies that were built by all kinds of different people, many of which have been mentioned. So we don't want to redo that. Okay, that is a fundamental thing. We want to use the pieces of it in super intelligent ways that we have to generate all of the things that we need, right? And so that's, to me, an incredibly important principle I want to get forward. So it releases every 6 months. It's well fast enough for what we need. There are parts of it that are released weekly related to medications that are coming out. It's robust. This is the 2019 AA release, and I put that up because it came out on Monday. And I said, well, I'm coming here on Thursday. Maybe I can update my entire environment for 2019 AA on Tuesday. And I did. Okay, so we take this gigabytes of data, rerun it into a model. It's running live in the model on the web. You can log into it. And what I'm going to show you from what was put out by NLM on Monday, because it's robust month after month. And by understanding it, you can build robust tools that work against it that generate all of these things. Okay, so what is the main point here? This is the main point. When I drew this one day, this is where I decided this was doable. What is it after many years of studying this that underlies UMLS that actually makes it really work? Okay, and what the core piece of this is, vocabularies come from far and wide, all over the universe, and they have these things called codes. Okay, and so SNOMED code whatever, or CPT code whatever, HPO, Go codes, almost anything that you can think of, foundational model of anatomy codes, okay? They have terms associated with them and types of terms, and they have concepts that they're mapped to in the UMLS, okay? But what happens is another vocabulary has codes mapped to the same concept, and that creates synonymy. And the concepts are mapped to each other through relationships that ultimately come from the vocabularies, but the relationships map concept to concept to concept. So if you look at this, you have, in fact, a graph. It comes in two tables. One table basically says, this term goes with this code with this concept. And another table says, this concept is mapped to this other concept with the following relationship. And basically have those two things, but working with them in a relational space means you join and 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 join. And this is one of the reasons why, I'm going to tease Olivier now, one of the reasons why some of the LLM APIs take 20 seconds to return, and the same API that I run in the graph database comes back in 80 milliseconds, right? The scale has reached a time we need to switch to other technologies. NLM hasn't done that yet. That was one of the drivers behind this, was my thinking about what do they have, how does it work, what is the graph model of it, could I build it, could you make it run, what would it do, could you traverse across all these vocabularies? And so I've been asking myself these questions for many years, and in 2017 I said, okay, it's time, and I built this whole thing that I'm going to show you. But it's based on this model, and this model is robust across all of those 100 vocabularies. Okay, and it means the vocabularies can interact. You can select for which vocabulary you want to be in, what types of terms, preferred terms. The STYs are semantic types. You know that all these things are drugs, all these other things are diagnoses. The semantic types tell you a lot about what you're working with. And then, of course, the concept relationships are every kind of thing. They're not is-a relationships. They're all kinds of other relationships that these vocabularies have that make it very robust. You have definitions there at the bottom. Then NDC codes are a particular thing that relate to drugs that I added off of the RX norm codes using one other table. So this is, conceptually was, okay, can we graph, literally take UMLS in an automated way, drop it into a graph with every update, and make a tool that lets you look around in there. What's it work fast? TTY? TTY is term type. So codes, you can say this code is a synonym type, or you can say this code is a preferred, it's the actual text, right? What type of text that is. So a concept can have multiple codes, a code can have multiple terms, right? These are just showing just the basic structure, right? But this is the basic graph structure, and then it blows out like crazy. one of the very important concepts, and I'm going to get back to a couple times, so I'm going to preview it now, is that multiplicity and how and when to know to deal with that multiplicity. So this is the thing that we're talking about. That it was built as a demonstration to show all these things actually can work. And now it's a robust tool we use in our team for all kinds of things, to understand where the vocabularies are, to search for them, all of the rest of it. And so you log in here with your UMLS license. We can talk about that. I'm actually a licensed distributor of UMLS, okay, which means I just sent them an email and they said, okay, and gave me a code, okay? But that means that you can build tools that send UMLS out to other people. And we can have a whole nother discussion about that in HuBMAP, maybe not for today, but there's plenty of ways to solve all of that. You know, as a distributor. So this is this thing, guest. Graphing UMLS enables search in dynamic trees. You know, this is like for me in my living room, so it gets a name like that. So I got myself a domain name that is that, created all this stuff. You saw when you launched it very rapidly, you come up and it defaults to the top of the SNOMED tree because it's been demonstrated for many years as one of the largest robust hierarchies across many, many things. So I chose somewhere. But it's a graph. It's not, in fact, a tree. Right? SNOMED is a tree, but UMLS
is a graph.
Well, SNOMED is also a graph, yes, but SNOMED is a relationship tree. But yes,
No, SNOMED is a graph.
it's a polyhierarchy.
Yes,
Yes,
it's a graph.
yeah, it's a polyhierarchy graph. Okay, we can talk about that all day long. But yes, SNOMED in fact is a graph. That is true. People think about it as a tree or a polyhierarchy. Many of them people think about our trees are actually graphs. So what I did is, there's a graph of all of this, right? So 80 million things, relationships, all these things. So you start here. What I did is I just switched. This was like the cooking show where I logged in and then I had another one in the oven. So I don't know if you noticed that, but I switched. And the reason I did that is because one of the things that this does is it leaves a trail that you can follow. And there's a particular trail I wanted to follow. And standing up here, I figured I'd probably get it wrong. So this is one in which I followed that trail and I'm going to follow it again. Okay, so if I say, well, I'm interested in body structure, because that's what we're kind of interested in here. And the slowdown that you're seeing, of course, is the video slowdown. But then I have anatomic and acquired body structures. I'm in SNOMED right now, okay? And I go out, I've reduced a bunch of these things. So there are many have procedures, okay? And so one of the tools is to kind of get those out of the way. So I've done that with a few other things. Okay, now it shows up in red the places that you've been, so you don't hit them again. So I've already been to body structure. It tells me maybe I want to go to the child of that, that's anatomic structure. I go down to the anatomic structure, and an interesting thing happens here. Really, I wasn't really interested in SNOMED. I was really interested in what's in foundational model of anatomy, but I started there. And so I go over to, in the same term, now with that same concept in two different vocabularies, they line up. Here now appear the other vocabularies that have the same exact concept. So if you look here in the middle of that, it says CUI C0702 something 076. That's the same. The reason those line up is because in SNOMED, that's been mapped to the same concept. Okay, so I can traverse across hierarchies or across vocabularies, graphs. That is very essential. So now I'm going to say, okay, well, let's go down to foundational anatomy because that's probably where this stuff is that I'm really interested in. And so I have the postnatal anatomic structure, which is to say it's after development, right, as opposed to pre-development. And I'm going to go down to an organ. And you can see I'm just following child relationships for the most part, solid organ. I bet you can guess where I'm going. A parenchyma solid organ, and a corticomedullary type of organ. And what a surprise, the end of the line is the kidney, okay? But this is just to show you the robustness of what is here and crossing all of these vocabularies as a very simple example. The other things that are in here just as demonstration, definitions. Remember I showed you the structure and definitions. So if I click on one of the dots, I get this definitions. This provides really interesting, tremendous feedback. That's all in the UMLS. We don't have to make any of that stuff up. So presuming that your curators are not just chasing data, but actually thinking about the data, they have dictionaries and so forth. So Now, sorry, I'm managing several screens here. Okay, so right. Okay. So now what I want to do is begin to show you a few other things in here. So I've gone back to the beginning of that. Okay. So this is just reloaded from yes.com. It comes up, right? There are some very interesting phenomena. And actually, for the purpose of this particular meeting, I did another edit to this week, which is I fully implemented the concept synonymy the way that I think it should work. Okay. And so I'm going to show you other features, but I want to show you that to make sure I don't forget. So this is a fairly advanced concept, and then I'm going to show you some simpler ones. But I just want to make sure that I don't forget this because I think it's one of the most important things relative to HuBMAP, whose problem, in my point of view, is to get on the map, get on the graph, right? I see it as much more of an annotation problem than a vocabulary development problem. I've got this thing, what the heck is it? Get it onto my graph somewhere. I've got this tremendous graph UMLS. I know how to work with it. I'm going to show you some more things that show it's amazing. The thing is to get on the graph, okay? And the way that you probably want to get on the graph is via search, by putting in a term and say, I want this thing, show me the ones related to that. So that's what all this stuff on the left does. I've just shown you the tree navigation. You can move around, you can move up parents, down parents, across other types of relationships, the full breadth of that entire thing. You can arbitrarily create these graphs that are presented as trees because that's what humans can handle, right? So I didn't show you any graphs that cause the other lines to occur. But if you look at guess.com, there's an example that shows you what happens when things start to connect together. It starts drawing other lines besides the trees that helps you out. That gets complicated. So I just want to make sure that this one concept gets across related to synonymy. So I'm gonna beat up on Olivier one more time for performance and now for results.
I have thick skin.
Okay.
I have thick skin.
But this is meanwhile my saying that the 30 years of curation are the most amazing thing ever, right? So I'm the grand supporter and micro critic, right? So here's the thing. I built this originally using NLM's API. So they have an API, you can get code to terms to codes, all these kinds of things. And there's a thing that they call crosswalk, which does that thing I was showing with foundational model anatomy. You put in a code, in this case, and you get back the crosswalk. And from that crosswalk, I've taken the terms that come when you put in the code ICD-10, C50. Okay, I didn't use a kidney example because I know this one really well. I worked in breast cancer. So, and have a whole nother consortium that's doing the same molecular stuff in breast cancer. That's not for today. So I put in ICD-10 C50, and then I just typed in malignant neoplasm breast there just so you know what it is. That result comes back, but the synonyms aren't correct. And this was another reason I built this entire thing, because it bothered me. Thank you. It bothered me so much that it wasn't correct. And so why is that not correct? It drove me bananas. And part of building this whole thing was to get enough familiarity with the graph and how things occur to see where that's happening. Okay? So if I go ahead and I put in, actually I don't do that. I put in something that I'm rather thinking about, which is breast cancer, because I don't know that the term is malignant tumor breast. I get the codes that actually say breast cancer, okay? And there's this tremendous set, okay? They actually have the word, they actually contain breast cancer, and it goes on and on and on and on, okay? It gets like, longer and longer and longer, breast cancer becomes a smaller and smaller component, okay? To give you some sense of what's there. So I happen to know that what I'm looking for, and Kati's telling me I don't have much time, so I'm gonna, instead of chasing through and looking for that, I'm gonna put in this C50 again, okay? And if I select the code, the terms for that, it turns out that it's mapped to more than one concept. And that's where the degenerate mapping is happening. Because that code in ICD-10 actually is mapped to two things. which breaks down the code being to a concept. So it's a degenerate concept. And so so if I just look for breast cancer by looking for all things that contain breast cancer, that's one thing. But what would be much more powerful is if I do that concept synonymy that we saw from NLM that breaks down because it goes through all this coding, right? And so where there's a divergent code, you have this degeneracy. What I've done is I've figured out how the degeneracy occurs because I'm working in paths in a graph that's much easier than in a massive set of tens of millions of things in relational database. In a graph, you can determine the pattern that causes degeneracy and control for those patterns. And it turns out that degenerate codes are only 3% of all of UMLS. All the rest only map a single code. But by eliminating the degeneracy, you get this result instead. So this concept synonymy now, I can put in any of those things that are represented across all of those vocabularies to get to the same thing. And so this is the thing that I really most wanted to show. There's many other things that this can do. You can, search for whatever you want to search for. If you search for something like BRAF, this is an interesting example because, I have to turn off the concept synonyms. These are all the BRAF things, right? If I turn off the synonymy, now I'm searching for things that just literally say BRAF in there, okay? Is that gonna work? Did I break it? Shouldn't be broken. Oh, it just takes a long time. There's many things that have BRAF in them. So one of them, you'll note, is zebrafish. Well, I don't want that. That has BRAF in it. Okay, so I can tell I give it certain clues. No, this is actually case relevant. BRAF is a thing. Do it only with uppercase. So Kadi's telling me it's time to stop. But I think the point is that we can go down all of these different ways down through this graph for all of the different things that you're interested in. You can start the tree from where you are. Okay, this is a degenerate code. So I have to say, well, where do you want to start? I can start this one in 4 places. Normally you don't see that, but the degenerate ones, you have to make a choice. And then you're off and running from there, same way that we showed to go out throughout the graph. I'll stop there.
Great. 1 to 2 questions if they are quick ones. Olivier.
Just for the record, NLM doesn't think of these codes as degenerate codes. There's a number of strings, a number of terms, and different vocabularies decide to package these terms into their own, they have their own flavor of synonym. And the flavor of synonym that you find in ICD might be different from the one that you find on another terminology. And NLM superimposes their own flavor of synonyms. So they can decide to break a set of codes that are in, or set of terms that are in ICD and separate them out. And they can decide to merge 2 codes from SNOMED into a single UMLS code. So that's what's called concept orientation. Jim Smith invented the word, I guess, a long time ago. And it just reflects that different terminologies impose different concept orientation perspectives on a set of terms.
Absolutely, and I thank you for saying that. Part of my point is that the robustness that's present allows you to choose the way that you want to think about it. And so the way that I chose to think about it is to say, the way that I'm thinking about synonymy, I'm going to declare codes that map to 2 concepts as degenerate terms or degenerate codes.
It's intended
to be that. It's intended to be because they're degenerate from that perspective.
Yeah.
And so that is the entire point, is that if I want to work in a particular vocabulary, I can. If I want to work across vocabularies, I can, but I have to make certain choices. I have to declare these things in these different ways. I can be as granular in that as I choose to be because it's so consistent.
You mentioned divergence. How do you protect the user from a possibility of convergence? So you might have the same term, but with different definitions used from different vocabularies that are integrated over UMLS. Say ventricle. You have ventricle in the brain, you have ventricle in the heart. How do you protect the user from misapplying the wrong term for their particular annotation requirement?
Well, the context gives you feedback as to which you're working with, but very often,
Yeah.
the term ventricle actually is defined at a level that it's both, that it really is the meaning of ventricle, which is a space, occupying thing. So very often you have that, and then you have mapped to types of ventricle. When you use this in that robust way, I should have left it open and tried to show you, but it's so deep that it's surprising. I've been playing with this thing for 2 years since I first built it, and it's surprising how often it gets that right.
And so typically there's 3 copies of ventricle in the UMLS, and in the FMA in the first place, there's the agnostic ventricle, if you wish, and there's the brain ventricle that's typically a child of the agnostic ventricle, and the heart ventricle is another one.